Morning, folks. I wanted to answer any lingering questions about homework 3 since it was due last night. Are there any questions about any of the parameters necessary to set up the ADC? There's a lot of obscure stuff, and I gotta say that the timing setup stuff is so hard to understand that there's an element of magic to me in setting it up, but let's see, describe the threads you use and their function. That's really what these questions are about, is to make you read the documentation. Think about the documentation. In fact, there's basically no right answer to most of them. There's probably the one that generated the most interesting comments on Piazza was 4. And that is because it's the specification is rather open. And the main thing is that if you're sampling at 8 kilohertz, it's not going to take long to go through a 256 table. In fact, you're going to have to go through the table about 32 times in 1 second. And so then how do you turn it off again? You have to start the DMA in auto mode and then turn it back off again, presumably as a 1 second counter in a timer in a thread. Although there's probably other ways to do it also. Any questions on this? Anybody, anything you want to talk about? Yes?
Okay, I have a couple questions about using the DMA and SPI. So when you hook up the DMA to, say, timer 2, where the DMA gets run off timer 2 interrupts, if you then disable the DMA later, what happens when the next timer 2 interrupt happens?
Nothing. So if you have timer 2 set up, to produce an interrupt flag every 8 kilohertz. So that's 5,000 cycles, every 5,000 cycles at 40 kilohertz. And you're using the flag to trigger a DMA. Oh, man. Trigger a DMA transaction, a cell transaction. Then if you turn off the DMA, this flag just keeps getting set and nothing happens.
Okay, so you don't have the system continuously reset? No,
not unless you turned on the interrupt flag. You have to start the timer, but you cannot configure the interrupt. So, for instance, if we go back and look at, let's see, what example? Cricket call generator. Someplace in here there's a DAC and the development page, DAC DDS, source code. So we go down here to where we turn on the timer. So we're going to turn on the timer. T2 on, T2 source internal, prescaler to 1, 200 cycles, or you're going to be probably much slower than that. You do not configure the interrupt. Because if you configure the interrupt, then the interrupt handler will notice the flag and take an interrupt. And if you don't have an interrupt handler written, if you don't have an interrupt service routine written, the default interrupt service routine is reset. So you don't configure the interrupt, you merely turn on the timer. Yes?
Okay, so question number 2. So the DMA is writing to the SPI channel. The DMA, I need to write 2 bytes at a time because the SPI channel is taking 16 bits for the DMA.
Right.
But when the DMA is it going to write one byte to the next byte, or is it going to write them both at once as a short? Because word that writes one byte and the next byte, then the SPI channel might output them separately.
That's an interesting question. So, question is, how does the DMA actually write values? And the answer is that it writes a byte at a time, as far as I can tell. And so what happens when it writes one byte to an 8, so it's writing it 1 byte to a register which is 16 bits long, what happens? And it writes the low order byte, then the high order byte, because it goes in memory order. And the SPI is triggered only after the second byte is written. But why? How does it know that the transaction is done? And I suspect it is that the SPI is in 16-bit mode. It knows to wait for 16 bits. But that's a detail I haven't played with. So what would happen, for instance, if you sent a 16-bit values and put the SPI in 8-bit mode? It would probably transmit on every byte and skip every other byte. Setting up the DMA for a 2-byte transfer, sending it to a framed SPI, in fact works, because I tested this. And so I don't know what the interlock mechanism is. That is even below the level of the hardware reference manual in terms of abstraction. So I don't know the answer to that. Good question, though. What else? So you are going to turn on a timer. You are not going to turn on a timer interrupt because there will be no interrupts. There will be no interrupt to send audio, at least. Oh, yes. One other chunk of bad silkscreen. It turns out that RB12 does not exist on the package that we're using. Neither RB6 nor RB12 exist on this package. They exist on the 150 but not the 250, because on the 250 there's a USB interface that has to have some I/O pins, and these 2 bits are used for that. So RB12 does not exist on this package, neither does RB6, so you can't use them for anything except USB. So back to homework. Any other questions on the homework? First question is just convert it. That's easy. Write the code necessary to send 1 second of DAC. Does anybody want me to go through the DMA setup code again now that you've had a chance to think about it? Is that useful? Okay. So we're going to go to the DMA page and look at the first example, which sends bytes to a I/O port. And because I wrote this fairly early on when I was writing code, I put all this setup stuff in main. Don't do that. You're using config.h to set all of the config parameters for the CPU. You don't put any of this stuff in main. In fact, you put as little code in main as you can, put everything else in a thread. We're defining a unsigned car sign table. This is cars because I'm sending 8 bits to a 8-bit DAC. And then setting up the DMA channel. Notice I'm opening timer 2 here, but I'm not turning on the interrupt. No interrupt turned on. Then we open the channel. I opened it in auto mode. You may or may not use auto mode for your sound effects depending on how you write the table. If your table contains one iteration of the sound effect, ping, 30 cycles of a damp sine wave, then you'll traverse the table once and you won't put the system in auto mode. And then you don't even have to turn it off. It just auto turns off. If you are going to put out a sine wave burst for a half a second or a second, you probably can't make a table long enough to do that. You'll run out of memory. And so you're going to probably put the DMA channel in auto mode. It depends on the effect you want. Do you want to go through the table once and stop, or do you want to iterate the table until an external event stops?
So we can't play multiple sounds at once with the system, right?
You cannot play multiple sounds at once because you're playing back a table that you can't compute with. So, but I think what you're thinking is, I'm inferring what you're thinking is, what happens when you have a ball sound interrupt another ball sound?
Yeah.
What should you do? Is that what you're asking, really? Mm-hmm. And the question is, think up something. Stop the sound and start a new one. Or continue the original one until it's done. Do what makes sense in your mind. Then we have to set a channel transfer function, which is going to be the source, the destination, and the length for each one. So we're going to set up for a certain DMA channel, we're going to tell it where the table is and where the destination is. And again, your destination is going to be SPI2 buff. Destination to be SPI2 buff. The table size in this case is in bytes, and the units of this transfer is in bytes. For you, depends on what you're going to do, how you're going to open the channel, but probably this will be the sine table size times 2 because you need to send 2 bytes per entry. The destination size is 1 byte here, but for you it will be 2. And the number of bytes per transaction, in other words, per T2 trigger, would be 2. Question on that? Then we have to tell the event control module for the DMA channel what to wait for. We're going to set up a start on the timer 2 interrupt request, but a reading of the hardware reference suggests that there are really 2 sets of interrupt flags. There's the interrupt flag that the interrupt controller notices and deals with, and then there's an event flag that the DMA controller can use, which is always set regardless of whether the interrupt is turned on for the timer or not. So this says, notice when the timer times out, do not take an interrupt, just start the DMA channel. And then we enable the channel. And I enabled the channel here because I wanted this thing to play forever. This is a signal generator. It's supposed to just play the rest of the day. I actually did this for a research project. You are probably going to actually enable the DMA channel in a thread. When there's an event that occurs, a ball impact, a ball going off screen, some event you want to emphasize with a sound, in a thread, you're going to enable the channel and immediately the sound will start playing. And it will play. If you open in auto mode, it will play until you disable the channel manually. If it's in single shot mode or normal mode, it will play the table once and stop. So for you, this will be a programmed function in a thread. So that's the DMA side of things. Then there's the framed SPI side of things, where you have to set up the framed SPI channel. Again, any questions on this? So the framed SPI channel for the framed SPI channel, you're going to open SPI channel 2. Channel 1 runs the TFT. You're going to open it in mode 16, 16 bits, master mode, clock and reverse phase. It turns out that's what's correct. As I may have said once before, the only way to figure out whether to reverse the clock phase and phase shift at 90 degrees is to try it with the chip you have. But as long as you stick with microchip SPI parts, which I try and do, this seems to be the parameter that works. We're turning on framed mode and framed polarity so that the chip select stays high and drops low for one cycle before the next SPI transaction starts. Sorry, that's normal mode. In the mode we're using, it goes high and then stays low, and the data is sent for a small amount of time after it goes high and then low again. However, to make this work, you have to use the SS2, the slave select 2 line, which is on RPB10. And so we have to modify the connections to the DAC to come off of RPB10 and then up to the chip select line of the DAC. So once this is set up, once the SPI is set up, once this SPI is set up, the contents of the interrupt, what interrupt? There's no interrupt. With a DMA controller, this interrupt is going to be gone. There will be no transmit. There will be no check to see if the bits are ready, if the channel is ready. There'll be nothing. There'll be nothing, because when it's all set up, when the SPI is in frame mode and the DMA is sending a table to the SPI, then all of the trigger hardware, all of the trigger logic for the SPI channel is in hardware, not software. So the table will send 2 bytes. The SPI will notice that the 2 bytes are sent, toggle the chip select line, the transaction will happen to the DAC, sound will come out, and then the system will sit there until the next timer tick, which causes a transfer of 2 bytes from the table to the SPI, and the next value comes out. Completely in hardware, no software. No interrupt service routine, no nothing. No overhead. No software overhead. Questions? What else on Lab 3 now?
I had a quick question about the ADC setup. So you start with your sample code.
Uh-huh.
It was just one of the parameters that I was kind of confused on what it did. So if you could open up.
Well, let's see. ADC. Sample code. Which one? Oh, I know which one it was. It was the PIC development board.
Yeah.
ADC.
So
Example.
you basically set up like 5 different parameters.
Yeah, it's a mess.
Yeah, in parameter 3 there was one that confused me. ADC sample time 5.
Oh.
Right in the middle. Yeah.
All right, so this is the line that I said is just awful to understand. And the reason is that it's specifying 2 different times. It's specifying a sample aperture. How long should this sample and hold switch be closed for? Bink, open again. And it is setting a conversion clock separately. And I set this up for the minimum time that the system could take at 40 megahertz. So, but decoding how this all works is a horrible mess. So I would say, and what I said last time was, just use this the way it is until you read the documentation 25 times. Just use it. Because I had a lot of trouble figuring that one out. I mean, days. What else? Yes?
While we're here at the parameters, there's another one I wanted to ask you about. So one of these parameters, you were disabling the ADC's self-test calibration mode.
Right.
I get that you're disabling it, but I'm not sure what it does.
So it puts a known voltage on and then asks what count comes out. But I'm disabling it because I didn't want to figure out, when I wrote this, I didn't want to figure out the timing required to make that work. So I just disabled it. And for controlling an analog control, you don't really care if it's off by a few percent because you're going to compensate visually for that anyway, and it won't be off more than 1 bit anyways, even if it isn't self-calibrated. There will be a little zero offset, however. There's a few millivolts of zero offset, which again you don't care about for the control example that we're doing. So that I haven't played with.
2 questions. First one is the ADC conversion clock that you were talking about.
Uh-huh.
You said that is for 40 megahertz, that's the minimum time. So we're going to increase the system clock, I believe, right? The frequency.
You can.
So if we do that, it's not going to adversely affect that.
Might fail.
All right. So So that's one thing. And the second thing is in the DMA code that you had add star and lat b, I believe. I'm not clear on what's happening with that.
So this is a destination pointer. Just as this is a pointer, this is a pointer, right? This happens to be a pointer because sign table is an array, and when you use the name of an array with no index on it, what you get back is a pointer to the array. Lat B is the name of the register that is the output latches for the B port. You are going to be using SPI buff, 2buff, right hit there. This says make it a pointer, and that just says it's a void pointer. It just says don't care about the size of it.
One more question. So for the timer, you said that there's two flags. One is the interrupt flag, and the other one is the DMA event flag. And does it mean that when the DMA begins transmission, if we clear the flag for the event flag?
If you clear the flag,
Like the event flag?
I don't know. I
You
don't
said
think
there
so.
are two flags.
There is a shadow flag. There's an interrupt flag which is noticed by the interrupt controller, and there seems to be a separate flag, if I read the hardware description correctly, that is noticed by the DMA controller.
Okay.
You can't clear that. There is no call to do that.
But DMA is doing it by itself. Right?
Yes.
So since there are two flags, and I don't think it matters if you configure the interrupt, right?
It does matter, because if you don't write an interrupt service routine, the system fails.
Oh,
And you don't want to write an interrupt service routine because it takes time.
okay.
So do not configure it. Right. This is a software construct that has hardware implications. Don't do it. What else? Well, we are about between 2 and 3 weeks away from final project description time. Due on homework 5 is due on the night of your lab section, on the night before your lab section, the week of 10/9. So that's the week you get back from fall break. So that's 2.5 weeks or so. So I thought maybe we ought to look at this assignment, because you need to get some headway on this. You need to start now. We're going to ask you to put in an initial specification design for your final project. And we're not treating this so much as an evaluation event, and as an evaluation as a feasibility determination. So what we want to see is that you've thought it through well enough that we can figure out if you can actually do it or not. And is it too hard or too easy? So the more work you put into this, the better we'll be able to ascertain whether or not this is doable. It's going to be like a binary. It's an acceptable, it's unacceptable in terms of the amount of work. If somebody hands in 3 lines that says, we're thinking about doing something with video, that's going to be just a 0. But if you write a one-page description of what you want to do, it's not an evaluation thing. It's, can you do it? How are you going to do it? Does anybody care? So we want something like description of the project at a high level, not necessarily talking about the hardware so much as the rationale and the functions. A paragraph of standards relevant to your project, and everybody is using some standard. Tentative parts cost list. You're going to be limited in the amount of money that you can spend. I'm thinking about raising it to $125 this year from $100. Probably will raise it to $125 to account for inflation. It's been, I don't know, 5 years since I raised the cost or so. So, inflation. But it should be, I try to set it at a level where the cost is low compared to the cost of a textbook, and where clever thinking counts more than brute force money spending. We have to, this is a ABET design course. ABET and I care about societal impact. If there's safety considerations, you're going to do a high-powered laser cutter. Oh man, are there some safety issues with that? You need to address those. One year we had this really cool project, which was a automatic grapefruit slicer that went around and cut out all the sections of a grapefruit with a big knife. Chunk, 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 chunk. It had, the driver was a couple of servos that they got out of the drawer of a disk drive. So it was wham, 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 wham. For that one, there had to be hardware cutoff switches. No stinking software here. When you lifted the top off this thing, the power was cut to the CPU. Period. No question. And it was quite safe, but you watch this thing running, it is terrifying. Safety considerations, human factors. Does it require discrimination of fine color levels? 6% of the male population is red-green colorblind to some extent. That says that 1 in 6 of the males here can have a color problem, and you have to think about that if you're designing a color interface. It's a gene-linked thing, so females are like 0.01% red-green colorblind. Intellectual property considerations. Are you going to redefine, are you going to redo duck hunt with a PIC 32? If so, there's IP considerations. What are you going to do about Nintendo's copyright? If you think you need IP consideration, if you think your system is novel enough, then you should write about that too. Probably going to want to put in a block diagram or pseudocode or something that suggests that you know something about it. Oh yes, also, any RF transmitter has to have reference to FCC regulations. You use a Bluetooth module? I want to know. I want to see the FCC code section that regulates Bluetooth. It's called Part 15. You'll love it. It is a piece of work. I want you to reference that completely. Block diagram, tentative source code if you have it, tentative schematic, maybe, parts list with specific parts numbers. As much detail as you can at the first stage of a project, probably a couple of pages, maybe as much as 5 pages, not more than that. again, this is a way for us to be able to tell if what you're doing is reasonable and to give you some feedback on what might make it more interesting or more doable, or maybe it's too easy and it needs to be beefed up a little bit. There will almost assuredly, there will be a bonus for finishing early. And I think I showed you this lovely formula. It's the round of 2.7 times the floor of the number of days to the half power. But there's a table here which gives you the point bonus for finishing early. And we will almost assuredly extend the deadline from the last week of class to approximately to study week, to study days. So there'll be a little extra time at the end of the semester to demo. But I won't have the exact dates yet. The day that the project report is due is determined by Cornell policy. Every class has an assigned time for final reports, which is based on the starting minute of the class during the day. So whatever Cornell says is what we will do. I probably won't know for another couple of weeks yet what that is. It will probably be about the last day of demos, or maybe a day or two after, but could be near the end of finals. It just is luck of the draw. So we will do whatever Cornell says on that. I'll look it up soon. Your final project report will be a web page. There's a bunch of very specific things you need to put into that web page, which is in the form of a rather long and involved outline. So you need to start reading this fairly soon, because it may be that the final project assignment itself will partly determine what you want to write for the proposal. Yes?
I just looked it up. Cornell's already published how to calculate your cost.
Yeah, and when is ours due?
It's December 6th.
December 6th! That's only, yeah, okay, that's like, let's see, the last day of classes is the 2nd, I believe, right? It's Friday, December 2nd? Friday...
December 1st.
December 1st. Oh, well, okay. So December 1st is a Friday. That means that the demos will be the 4th, 5th, and 6th, and the report will be due the night of the 6th.
It says that it has to be due at 11:30 a.m.
I know, 11:30 a.m. I'm giving you a break and make it 10 at night. We'll make it 12 hours later than they specify, so that people that are in the afternoon lab can actually write it up and submit it. But basically, you're going to have the report done before you demo. Basically. So, this suggests multitasking. When you're not in lab, you're writing. Yes?
If you demo early, is the report still due before you demo?
I didn't say it was due before your demo. I said it is due on the 6th.
Okay.
If you demo early means with relationship to your last scheduled lab. Not with respect to December 6th, but with relation to your last scheduled lab. So if you have a Tuesday lab, then your due date, your official due date, is Tuesday the 28th of November, and to get early points, you have to demo before then. If your lab is December 1st on Friday, then you have to demo before that date to get early points. Towards the end of the semester, it's hard to remember that the Tuesday lab starts final project 4 days before the Friday group. 3 days before the Friday group. But that matters. So any questions about this assignment? This is, spend some time on this homework. It's not too soon to start kicking around ideas to say, you know, what are we interested in? Do I have a collaborative project that is going to be with another lab? There's one group already that's told me they want to do some collaboration with a robot group. If you're involved in, in MEng research or outside research that you think might be, for which microcontroller might be useful, then pitch the project to me before homework 5 is due to see if I think it sounds like a valid collaboration. If it is a valid collaboration, then we will waive the budget restriction. You can spend whatever you want. Presumably funded from the research grant of whoever else is participating in this. This is explicitly designed to encourage collaboration outside of the course. Yes?
Could you do this at the same time as another course's final project and have like one big project for both courses?
You can, what you're asking is it possible to do one project that spans 2 courses? Yes, with conditions, as usual. The conditions are that both instructors have to agree on it, and that there has to be a piece that is clearly related to course A and a separate piece of work that is clearly related to course B that happen to bolt together. So for instance, if you were in Joe's Embedded Linux course and you wanted to do a project that took a PIC32 and hooked it to a Raspberry Pi, and there was enough work for 2 courses, that might work. What did you have in mind? AI. How would that work? What would you do for an AI course in microcontrollers? That's an interesting idea.
Well, we haven't thought of like a specific project idea yet, but like if our hardware, software had some sort of AI component in it, some sort of autonomous.
Yeah. Okay. I mean, I might buy that. That sounds reasonable. I would say that doing large-scale convolutional networks is not going to happen on a PIC32. But a small spiking neural net running a robot cricket to follow a sound might. Now, whether or not that counts as AI or not, I don't know. It's a good embedded project. Any other ideas that might require collaboration with another group? Now's the time to start thinking, folks. Chat over dinner. Chat when you're sitting around in the lounge. Start hallucinating ideas. And, I mean, a lot of them come up this way, right? We need a fart intensity detector. Yeah. Yeah. That was a good project. but it caused me some grief. So start thinking. What do you need around the house? What do you need for racquetball? What do you need for music? What do you need out in some other context of your life besides microcontrollers? What else do you do? What else do you care about? Hook stuff together. Make a project that incorporates some other interest into this course. That's what makes good projects. Could be robotics, could be 3D printing, could be I had one that was really good. The guy who said, people kept coming into the kitchen of the fraternity house and messing the place up. We want a card reader for the door, the kitchen door. So he built one. The RFID reader. He built his own RFID base station out of op amps and wire, and made a card reader that would take Cornell ID cards, and made a bolt system for the door and hung the whole thing on the door of the fraternity house. That's cool. Solves a real world problem. People figure out how to jam it open, of course. Okay. Anything else? Any more questions about Lab 3?
Can you talk about overclocking?
Overclocking, yes, sorry. So if you go to config.h, if you go to config.h file, you can modify that. So right now the input phase lock loop divider has to stay at 2 because the input to the phase lock loop has to be about 4 megahertz and the oscillator is at 8 megahertz. The multipliers you can use are not arbitrary, but are most of the numbers between 2 and 20. So you could choose 15 here, or let's see, can you even go higher than 20? I think you can go up to 22. You'd set the multiplier to whatever you want, set the output divider to a number then that takes you into the range of 60 or below. I don't think you should go above 60, although you could play with it. As I said earlier, I've tested CPUs up to 80 megahertz. None of them work at 80. A few of them work at 70, and many work at 60. I'm not going to let you sort through CPUs for one that works at 60. Yours either does or it doesn't. Maybe I'll normalize by clock speed so that overclocking is not so important. Because I don't want to get people sorting through CPUs. This is a huge waste. I'm going to normalize by clock speed. Don't worry about overclocking. Set it to 40 or 50. They're all guaranteed to work at 50. It's impossible to set the phase lock loop to 50, but you can set it to 48 if you want to speed it up. But I'd rather you concentrate on other stuff, like making the collisions efficient. Efficient C coding. Resource restricted C coding. You don't have much memory, you don't have many cycles. Use them well. Anything else? I'll open up lab tomorrow by request in the morning.